You didn't ask enough, you didn't learn. Okay, it's still on time to learn it, because we will have to take the limit in order to understand deeply what is going on. So I'm going to do the Higgs mechanism, as I said now, carefully, slowly, rigorously, which I outlined yesterday. And then we will see once again how the Goldstone subcase emerges. Okay. So today, what we said yesterday, we do systematic analysis. Higgs mechanism. And as always, you see how I'm sort of doing it? I'm always doing it progressively from simplest to more complicated example, and then maybe giving some kind of general outline. So, which means that we start with U1. Which is exactly the examples that we took before, except now we will ask that when phi transforms, there is always Q, right? In charge associated with U1, we took it to be 1. And now we are going to ask that alpha is alpha x. So we have a gauge symmetry. The Higgs mechanism has to do with the gauge symmetry. This is now a function. So I have the same potential as before. Let me put the half here. Sometimes I will, sometimes I won't, depends how I normalize. Minus V of phi. Minus, of course, the kinetic energy for the gauge meson field that I just introduced by writing the covariant derivative. There is always Q in the covariant derivative. Amelia is here, so you better. You're okay, good.
This is the Lagrangian.
Sorry?
This is the Lagrangian or...
No, Lagrangian, yes, thank you. Of course. It's a kinetic energy, actually generalized kinetic energy, potential, and of course kinetic energy for the gauge field. The potential is always the same, right? Who cares whether the symmetry is global or not? Local or not. Q in this case we can take to be 1. And, well, I can write it once again. V of phi is lambda over 4. Phi squared minus V squared, everything squared. And I can write phi is e to the I g over V phi, real part, which I write as V over h. I am perturbing around a non-trivial vacuum expectation value. And then we said yesterday, well, now the symmetry is a gauge symmetry. So I have a phi field and I have an A field, right, with its proper indices. But I can always gauge it. So I can introduce phi prime, which is e to the minus g over v times phi, and then becomes v plus h. I can gauge a Vg, we say. I see that it cannot be physical immediately. If there is a gauge symmetry, the phase will not be physical, okay? I'm guessing it from here. Why? Because A will transform into A mu prime, which is A mu minus 1 over G d mu G over V. So I can work with phi prime and A prime, you agree? I will not give them the name prime, because it's terrible to write prime. But what I will do, I will call this phi, let me give it a name still, it will be useful for us to keep it, phi u, for unitary, which is often called a unitary gauge, or a physical gauge, I could call it phi. Which tells me, in this particular case, so I'm fixing the, so let me call this a unitary picture. I want to see what is going on. I have isolated the physical degrees of freedom, and I find out immediately. Now, of course, you can say, how in the world did you eliminate the degree of freedom? How could you gauge it away? We saw it yesterday, and we'll see it now. Covariant derivative becomes d mu minus ag a mu, I will not give it a prime, times v plus h. And therefore, from here, 1/2 d mu phi squared is simply d mu h squared with a half kinetic energy for this field that now we can call it the Higgs field. Okay, the existence of this field was no, it should be called maybe Goldstone. The Goldstone boson should not be called Goldstone boson. It was Nambu who saw them before. It's somehow the second person tends to get the credit, okay? Most of the time. It's interesting because people don't notice when the original work is done. We should have called this a Goldstone Higgs field because the existence, remember, I found it already in the Goldstone case. Anyway, this is called the Higgs field. And people sometimes associate and they say Angler Brout Higgs field. Angler got a Nobel Prize. They didn't have the Higgs field. Have a look at the original paper actually. This is wrong. Okay, people don't look at the original. Plus, what do I get? I get 1/2 g squared v squared a mu 1 plus h over v squared. From this potential, remember we wrote this potential many times, I will get that mh squared is 2 lambda v squared. This you know it in your sleep. This is the beauty of the Higgs mechanism. The mass will come out magically, okay? Higgs is the source of all masses, including its own. So the Higgs mass is proportional to V. The gauge boson mass is proportional to V. All the masses in the world will be proportional to V because that is the only scale here. Everything else is dimensionless. So, what are the consequences? The first one is that MA is GV. I got a massive gauge field what I wanted. This will be my Z boson or a W boson. Let's think of the Z boson, it's neutral. At this moment I have a sort of neutral guy. So I can think of the Z boson. So at first glance I'm very successful. Besides that, another important thing, notice the second term when I expand. From the second term here, what will I get? I will get 1/2 MA squared A mu times 2 H over V. I got an interaction of the Higgs with the gauge boson. But this I can write as half goes away as G MA A mu times H. I could have guessed that the coupling was going to be dimensional because this has dimension 1, dimension 1, dimension 1, there's dimension 3, so the dimension will enter. But what is important here, that this is precisely the mass of the gauge field. You've just learned what we can generalize as a theorem, and we will show it for all the particles that are involved. The coupling of the Higgs to anybody is just like gravity in the small momentum case. In the Newtonian picture, it is proportional to the mass. The coupling is universal in the sense that it's always the mass. Of course, the value of the mass is not universal, it's individual. Each of us has a different mass, okay? It's not one and the same coupling. In the case of the gauge boson, you have one coupling, which is the gauge coupling. In case of the Higgs, its mass, it varies. It doesn't matter how fast the particle is. Notice, the coupling will be proportional to MA. So if I ask you, what is the coupling of the Higgs to the photon? Quickly? Zero. Photon is massless. But how did they see the Higgs? Do you know how they saw the Higgs? The original decay, what they saw?
Two photons?
So how could they see the two photons if the Higgs doesn't couple to the photons? We'll have to understand that.
Case in top.
Sorry?
No.
No?
In
So,
case in top. Like,
actually, it can couple to fermions, fermions can couple to the photons. So when I say that you don't couple, I mean you don't couple directly. We all couple to everybody, indirectly. No, it's sort of, that's the beauty of the quantum theory, right? That, okay, there are virtual things going on, okay? But we'll see that as the time goes on. So, this is the way Higgs and Weinberg especially looked at the Higgs mechanism. It is Weinberg who will introduce the Higgs mechanism, the standard model. If anything, this should maybe be called Goldstone Higgs-Weinberg particle, okay? The particle that we saw is actually the Weinberg particle. It's Weinberg who wrote its specific properties in 1967. It was discussed by Salam, but the specific property of the Higgs was spelled out in 67 physical letters by Weinberg. The thing is, okay, and Nicolas noticed the other day, well, it seems that you did something good, but at the end you failed because you got a Broca theory. This guy is massive. Remember what we found out? That delta mu nu, the propagator for a Broca field, that's what I have here, will be minus I over q square minus ma square, g mu nu minus q mu, q nu over ma squared. I still have this divergence ma going to 0. Something is wrong. How can that be, right? Or if you wish, this goes as 1 over ma squared when q goes to infinity. This is not good. We want to propagate it to vanish because we'll have to integrate over them. And we'll never get finite result. So we are stuck. This is the great success of the Higgs mechanism. It gives gauge boson a mass magically out of nothing. I started with a theory which was symmetric, and then lo and behold, things changed. The ground state decided to break the symmetry, but I still don't know how to compute.
I have a question, just some question about the photon interaction. We said that because the mass of photon is 0, we don't have interaction with Higgs field, but...
well, I'm suspecting that. We'll have to discuss it. We have to do it in the standard model. It was just a remark en passant. This is not the moment to understand it, really.
I see.
Because there is no photon here.
Yes, okay.
I'm guessing because I'm finding out, okay, you know, this is a desire to generalize. We like to do that, okay? If the Higgs is to couple to the particle should have a mass. Notice that the Higgs couples to itself. Remember that the Higgs couples to itself through lambda? Right? But lambda is proportional to the mass. So it's kind of nice. Higgs is coupled to itself also to the mass. Just to keep that in mind. I'll comment on that later. So let's leave the photon if you wish, unless it's urgent when we actually study the standard model. Okay.
Yeah, because what confused me is that we construct the theory here that we have massive A, massive M.
Right, there is no photon yet, so don't be confused.
It's a contradiction.
Just wait.
Yes.
Right. There is no photon here.
Okay.
No, I'm guessing. If I were to be able to successfully generalize this to a physical world in which there are fermions, quarks and leptons and photons and so on, I'm guessing Higgs is not coupled to me unless I have a mass. Because what it likes to do, it likes to give you the mass and then immediately couples to it. You see, it's coupling from the same term. If the Higgs were not to couple to this, it wouldn't give it a mass. Because they always go together, Higgs and the vacuum excitation value. What is the Higgs? It's this guy. This is very important. He goes always. That's the definition of the Higgs. Remember it. You have a vacuum expectation value. It may be a complicated vector in some space. There will be a particle along the same line, always. And we do some example to see that explicitly. Okay, in the U1 case, remember, there is no group theory here, only physics. We are not learning the topology of the vector. So this is a success and a failure. The theory seems to be renormalizable theory. Remember, renormalizable, I just call the theory that it's finite, if you wish, not finite. And really, there was no progress for years. That's amazing. The greatest mind of the time worked for the next 5 years. There will be a complete impasse until a young student at Hoft goes to a Cartier summer school. And actually, I've heard this from Gervais. Gervais was teaching at the school. He says when he arrived there, he didn't know basically anything in 1971. A year later, the history was made. In a year's time, at Hof would single-handedly solve this problem. But I won't, of course, give you the complexity of that non-trivial work. What I will show you is that we have an elegant way of changing the propagator. I need to change this propagator. This is not good for me. So what I'm going to do, I'm going to show that part. I'm going to find a well-behaved propagator. And then I'll do some simple calculations, and then I ask you to believe me that this can be generalized to all orders in perturbation theory. And the trick is very simple. So this was a unitary gauge where I have explicitly eliminated this degree of freedom. And Hof said, well, let me keep G. If eliminating G doesn't work, let me keep it. Let me write once again. Which really what I mean is this. There are other terms. I'm going to ignore interactions. Remember, I just want to look at the propagator today. So let me ignore the complicated interaction of this field to other fields, okay? Why do I want to keep it? Because I know at Hof, going back, I don't know what went into his mind precisely, but obviously there was an analogy with QED. QED worked beautifully because of the gauge invariance. And you fix the gauge, you got a nice propagator. Remember, before you fix the gauge, there is no way of having the propagator. It's not well behaved. You repeat it as a homework. So let's try to do the same. Well, if I'm keeping this is not a physical degree of freedom, but it's okay. We've done it before with the photon. We wrote photon as a mu. So let me keep it. What I noticed that there is manifestly a gauge symmetry, G going into G plus V alpha, and A mu going into A mu plus 1 over G d mu alpha. This, of course, is a function of x. The symmetry is there. That's the original U1 symmetry. You see, we often say that the vacuum expectation value or the gauge boson Marx breaks the gauge symmetry. That is not true. I even make that statement. And I will make it maybe in the future. That's a careless statement. It is true if I were in this picture, in the unitary picture. It is true physically. But the gauge freedom is not a symmetry. There is no charge associated with that. It is just the counting. It is the redundance of using extra degrees of freedom. So if I add more degrees of freedom, I will have a gauge symmetry. There has to be that, because I'm working with unphysical degrees of freedom. And I've added that degree of freedom, and of course. So what it means, in this picture, obviously, the H field is there, the vacuum expectation value is there. Well, let's write d mu phi. So this is d mu H plus I d mu G minus I G A mu V plus H. I will have the same V plus H, okay? Let me just look at let me forget the interactions, okay? Let me look at the leading piece. And let me write here plus interactions. which with the same interactions as there. Notice that because of this, the gauge field will have the same mass. So I will have a massive gauge field because 1/2 d mu phi squared is 1/2 d mu h squared plus 1/2 d mu g squared. Well, if I keep g, it's going to propagate the same way that the longitudinal and time-like degrees of freedom of the photon propagate. Then what I will have is 1/2 ma squared a mu, you agree? I mean, after all, absolute value square is this piece plus this b squared, but there is an extra piece, which is minus half will disappear, g, well, g times v is ma, d mu g, a mu. Remember what happened in QED. Okay, we have to think now. Okay, it's the time to pause and it's a moment to be sure that you understand everything. Okay, here you will stop me if my hand already did. Good. The timing was good.
There we said that it's unitary, so we transform it in phi prime that way. But there, how we transform phi?
No, phi is this.
But how we transform? I don't.
We don't transform it. I don't.
You don't transform it.
Why do I have to do it? I can. There is a gauge freedom. I can choose any which gauge I want. When I make this gauge transformation, I could have taken n minus 2 g over v, and I would keep it. I can. The theory.
Here you redefine phi. Let's say.
No, if you wish, by performing a gauge transformation. I'm using this freedom of changing the phase. This is what it was, the original gauge freedom. I was allowed to change the phase. And I'm allowed to change it at a space-time point x. Therefore, I can even use g to transform g as a function of x. This is, of course, a subtle point, so I let you worry, but...
So let's see. You eliminate g here, and you don't have g anymore, let's say, or...
Well, g is not there.
Okay, so...
There is no g. There is no g. I'm keeping it because, look, there is no longitudinal photon.
Yeah, I see, it's an extra...
Go back to QED. If you are having problem understanding this, go back to QED. Sometimes I work with a 4-dimensional photon, but there is no 4-dimensional photon. I just pretend. But really, I should eliminate it. If I were really into physics, I should work with a 2-dimensional photon. It's hard to do calculations. And this is what we actually do if we want to understand what is going on. We isolate then the physical degrees of freedom, which would be electric or magnetic field, or really the transverse component of the photon, because these are the only components that actually exist. Photon exists, but only as a 2-component object. G does not exist. There is no G here. It's just going to virtually propagate the way the longitudinal photon propagates, but it doesn't exist. It's a virtual thing. It's there in the loops, but not outside. You cannot produce a time like, if you try and look at the production, I can go and remind you, I hope you have understood that. If you look at the production of the longitudinal and the time-like photon, they cancel each other. You don't produce them. I can remind you of that. I mean, that's a basic field theory. Okay, that's Peskin, Schroeder.
But let me put it in this way. In the QED, G was the longitudinal component, which is a derivative of which is a component in the momentum of our field. But here, G is something slightly different.
It's okay. I think in a second. Let me go on for 2-3 minutes and then I'll go back. I think I can make a better parallel. Let me just say this. I'm going to write this. I'm going to integrate this by part. So we can write this thing as plus, if I integrate by part, ma g d mu a mu. You agree, it's the same thing. I am getting rid of the total derivative.
It's
Okay, remember what happened in QED when I worked with a photon. I keep on now discussing for another 4 or 5 minutes, okay? So suspend take a deep breath and watch, and then ask me questions in a few minutes, okay? In QED, I had 2 extra degrees of freedom, and I needed to specify the gauge. Now, what I have here is a massive gauge field. It has 3 degrees of freedom. But I'm working with 4 of these. I also added G, so I have 2 extra degrees of freedom which are not physical. That means I cannot find the propagator. If I don't fix the gauge, this is complete analogy with QED. QED, there was 2-dimensional photon, 2 extra degrees of freedom, I had to fix the gauge. And I could see there was no propagator. Notice that there is no propagator here. I have a strange mixture. How can I find the propagator when the scalar and the vector mix? I must fix the gauge. I have gauge freedom. I cannot work when the theory is a complete gauge freedom because I have not isolated the physical degrees of freedom. I can't work with this. I have to, it's like a Lagrange multiplier. If I have extra degrees of freedom, I have to take note of that. So here goes. So let's erase the unitary. Forget now the unitary picture for the time being. Actually, maybe let's forget that we did this today. Let's forget that we were smart. This was not smart. This is how you and I would have worked. You probably wouldn't have even noticed that you can eliminate G. It would come later. You have written the field as it is, and you have studied the consequences. The way you did it in QED, you didn't eliminate those extra degrees of freedom. So, I have to add a gauge fixing term, which I'm going to imitate what I did in QED. Remember what we had in QED? There was d a mu squared. I'm going to add the same thing. But I need to get rid of this. This is not good. I can't invert A when A mixes with G. I can't invert G because G mixes with A. I don't know what to do with this beast. So I want to get rid of this. The way I in QED, I got rid with the unphysical degrees of freedom and I can finally find the propagator. So notice if I write here this term, notice I have to invoke G. Anyway, G has to end up in the gauge condition. Dimensionally, it has to be dimension 2. This is a derivative. And if I put C here, notice that I will get the, what is this? The usual QED piece minus, notice 2xc cancels, I get no, it's good. MHE, very good. I get a minus sign, right? You are with me. Let me not look at my notes. I have my notes just to be on the safe side for if we continue computing. I will get minus MA G d mu a mu. I got it. Then notice I will have minus 1/2. This is C squared, so I will remain, C remains, MA squared, G squared. Now I can find the propagators. I've separated G and A. Let me erase this. This is not true what I wrote. This was true. We'll discuss this later, the Higgs with the gauge boson. So let me call this phi r if you wish. There was unitary phi r is renormalizable. It's not physical. Or just call it phi as you wish. Just want to emphasize that I am in a particular picture. Okay, the quadratic piece will look like this. We have to invert the quadratic piece. There will be minus a quarter f mu nu, f mu nu. There will be with the minus sign the extra piece. And there is a mass term. So you see, I have 5 degrees of freedom. One, of course, gets eliminated because, remember with the Proca we found out that d mu and mu was 0. And G therefore cannot be physical. There is 1/2 d mu G squared, kinetic energy minus 1/2 C ma squared G squared. Did you copy this? Can I erase this? I wish I had a bigger blackboard. I hate erase. You know, there is the ICTP lecture on Blackboard is the best Blackboard in the world. I used to lecture a lot in the 80s. Okay, that's how I fell in love in ICTP. This is why I'm here. I used to work at Brookhaven National Lab in the States, and I got invited. It was actually one of the first schools. I fell in love with everything here. And I fell in love with that Blackboard. You can actually lecture 1 hour and 50 minutes, that I remember, without erasing anything, if you're careful. You know, it's not that, of course, blackboards that you can keep raising and lowering, but the great thing here is that you could walk and lecture. Notice what we find out. Read here, mg squared xi ma squared. Or if you wish mg, no, small g. I tend to do, most books do, capital M for gauge boson fields. It's more often a convention. It's not important. So it's like saying at mg, let me use the privilege of the blackboard. It depends on psi. This cannot be a physical field. It depends on a gauge. For example, I can take C going to infinity. I'm allowed to look even into that gauge, and the guy will disappear. But that's a Proca gauge. We'll come to that in a minute. Now this, from here, I find the propagator immediately. You agree? D of G is I, Q squared minus psi ma squared. That you know how to find immediately. But you also know how to find this. You're going to love to do this for homework. It's the same exercise you started the course with. You did 2 things. You did this without this piece, and you did it without this piece. So now we put them together, and we find out that actually del mu nu of A, which I could call R. Let me remind you that I'm in a sort of renormalizable gauge, if you wish. Okay. It's often called an R gauge, or even, to be careful, RC gauge, to emphasize that we have a generic parameter C. I get minus I, Q squared minus ma squared. Look, I get, this is a physical particle. It has a pole at ma. The way the photon had a pole at 0, this guy has a pole at ma. This is where the pole should be at the mass of the particle. But look at the change now. You get the following. Okay, you will derive this. It's going to depend on C, and you will find Q mu, Q nu, Q squared minus psi ma squared. C or psi, as I call it. So I'll say a few more things which may help you to understand what is going on, just another minute or two, and then I want to pause. First, for example, let us look at various limits. For example, psi equal 1. Notice what happens when I take psi equal 1. There is a normal propagator here, okay, it's always there. But look what happened with this guy. This guy goes into G mu nu Q square minus MA square. It's called the 't Hooft gauge. 't Hooft is a brilliant calculator, not just a brilliant physicist, imaginative, not just a great physicist, also a great calculator. He does some mind-boggling calculations. You see, the danger of fixing C is that you'll never know whether you made a mistake. If you work with a channel like C, you know why it's convenient, because C has to cancel. There was a gauge symmetry, and I have fixed the gauge, but I cannot depend on which gauge I'm using. Because of the gauge freedom, I can use any gauge in the world. So the art, and that's what we will do next time, we'll actually show how C disappears in one process. This is called the 't Hooft, often called also Feynman gauge, because Feynman used to like it. And Feynman also was not a bad calculator, as you know, right? Well, he found shortcuts too. To calculations. C equals 0 is often called Landau gauge. Remember, then you get just Q mu, a projective piece, G mu nu minus Q mu nu over Q square, right? It's not very important. I'll never use it. I don't like this game. Notice what happens when C goes to infinity. What does this go into? Huh? This dominates and this dominates. So I get a Procca propagate. Do you agree? This limit is very interesting. Let's really write it. Psi equal infinity. In the psi equal infinity, what happens? I'm back to the Procca picture. The one in which there is no G, but notice there is no G if psi is infinite. In the psi infinite limit, I get Procca for A, and I get no G. G disappears, as it has to be. Maybe this will help you to understand what was going on. There is no G. I can always get rid of it by choosing a particular gauge. So this is how I advise you to think of the unitary gauge. You take the limit after the calculation, because they're infinities. And you will go crazy if you try to compute before the calculation. You first show that physics does not depend on C, and then you can take the limit of C going to infinity. Sometimes you can actually compute, if you're lucky that the divergence is cancelled, or you can control them. But it's highly dangerous. I advise you strongly not to go into this thing that drove Weinberg crazy for years, and why he says that to this day, his wife tells him, you couldn't even normalize as your fool. He said it. You couldn't even normalize your own theory, okay?
What do you exactly mean that there is no G?
There is no G. I cannot produce a G particle. There is no longitudinal photon.
There's already no G. But
No, but it disappeared. No, here it is. Here it propagates in the loops.
you mean that? Okay.
No, here it disappears completely. The propagator goes to 0 when C goes to infinity. So actually, I will do the calculation and I'm back in the Procca thing, which is dangerous. I don't want to do it. So I will never work in this gauge. I did a few times. Okay, I should tell you. I have a paper in which I remember with my collaborator, we found a way of, sometimes we were lucky that the divergence is cancelled and we could see, and it's nice to see that. But you and I will think of Procca, or unitary if you wish. This is a unitary picture, as a limit of C going to infinity. After we compute, not before. We won't work with Procca. When we want to compute loops, we have to work a la 't Hooft. Why? You can say it here already, the propagator is well behaved. This goes as 1 over Q square when Q goes to infinity. Manifest. Just keep C finite. So you can believe, I don't ask you now to really understand how the theory becomes normalizable, but you can believe I have a good propagator which looks very much like QED. And I have a theory which looks like a gauge theory. It's not exactly the same. It took a tremendous amount of work by 't Hooft and Weltman and other people, Ben Lee and Zanshu Stein and many others to complete the proof the way Dyson, you know, it was not trivial to do it in QED. It took Dyson's genius to do it to all this in perturbation theory. But the crux, the essence is to have a good propagator or propagator. So what we will have to do here in the rest of the course, when we want to compute something, we'll think in this manner, but when we want to understand physics, we'll go back to the unitary gauge. And then we'll say, look, there is no G when C is infinite. Never, just forget about it. You're allowed to forget about it. The guy doesn't exist. You're allowed to forget about longitudinal photon, it doesn't exist. But don't do it when you want to compute loops. Advice is strong. Let's pause now.
Is there a choice for to give unitary gauge?
Sorry?
Is there a choice for CSI for unitary gauge?
Yes, C going to infinity. C going to infinity is...
That is equivalent to...
That's equivalent.
Okay.
Obvious.
Okay.
No, but it's manifestly because I got Proca. Look, I cancelled it because I don't want to work like that. I got Proca, and I eliminate G, and that of course was the unitary gauge. In the unitary gauge there was no G, and the propagator for A was Proca. Yes. So, unitary gauge and I call it unitary because, you know, when the theory is physical, you have to show that it's unitary, and in this picture it's easier to see it, okay? It would be better to call it a physical gauge, if you wish, or physical picture. It's equivalent, C going to infinity. Because in this limit I get Proca, and I eliminate G, no G. I mean, at least one thing I should convince you, at least in one simple process, that the physics does not depend on C. Because here, at this point, it looks as a great achievement, but if the physics depended on C, then of course we wouldn't achieve anything. The essence of this program is to show the C cancels.
When you say
Nicolas.
it's good to keep a finite C, it means like we should keep it in even at the level of calculating amplitudes and then set it in that level? Or
Yeah,
it's already
whenever you
there?
have loops. At the tree level, don't do it. At the tree level, there is no reason to do it, because at the tree level, you should get the same result in the unitary gauge. But I will show you how it's good, how you see that at the tree level. Of course, I'm not going to do loops. You are just now learning how to do loops, right? So we can't do justice to this beautiful program in my course. That will come much later, at least next semester, okay? You need at least a few more months before you proceed. And then I would like to answer your question. It would be nice that I see a certain process, look at the amplitude, and show there how C disappears.
I have a question, but it's resolved a little bit. Here we, from the beginning, when we write an invention, we will consider maybe, let's specify those things. It's vector field and it's massive, so it's like W boson or Z boson, right?
Precise.
And
Think of this as a Z boson. I'll show you in the standard model how it actually, but at the moment you can just think of this as a, it's not a photon of it.
But the kinetic term for it will be much more different. Okay,
Well,
we read this. So this.
well, not really. Not really. Remember, C is just, if I want to see what is going on, I can take C equal to infinity to see physically what is going on. So I found a perfectly well behaved, a perfectly consistent propagator. It just was not useful to do calculations in the loop level. But I found it by taking, and then the kinetic energy is the same as for the photon, and it has a mass. In the Broca picture is the simplest natural extension of the photon field. Just give it a mass. To do the loops, keep this and keep this crazy G. You can now guess what happens is, by the way, what happens is that this ugly piece is going to have to cancel against this. There will be always two contributions that will have to cancel each other. Here. And you will see how nicely it happens, because you will say, oh, but here I have sort of derivatives, momenta are like derivatives, and there I not, okay, and I'll show you that the theory takes care of that in a magical manner. So once you see how magic takes place, you can believe that it extends to more complicated cases.
The gauge symmetry that we speak here is completely irrelevant to the gauge symmetry of the photon.
It's similar. No, it's similar. It shows you, and this is what Stuckelberg noticed many years before. Stuckelberg noticed that if I introduce some crazy extra degrees of freedom, I can maintain gauge symmetry. Gauge symmetry has nothing to do with the mass of the gauge field. As long as you have 2 extra degrees of freedom, you will recover a gauge symmetry. Photon. So summary. Summary. QED or photon MA0, so there are 2 physical degrees of freedom, but we work with a mu, which is d equal 4. Then we introduce gauge fixing, then everything is okay. We eliminate this redundancy by fixing the gauge. So this is QED. This is what we would call the broken U1, broken QED, spontaneously broken. I have now MA is non-zero, but I added G. MA 0, so there are 3 physical degrees of freedom. Here altogether, there is D equal 5. So I have to fix the gauge. I have complete analogy. It's just this you learned, so you never paid attention how you learned it. It was sort of one of the songs that you accepted. So you didn't even pay attention that you were introduced extra degrees of freedom, because they were there to start with. You know, whoever wrote it, it wasn't me. It's not my fault. But I would have done the same. It shows you what understanding means. When you are given things in the beginning, you accept them. And that's why it's so hard to get rid of prejudices. You only think when the new thing appears. Hopefully. Most of the time you don't even do that, okay? It's hard to think. So that means I have to add gauge fixing. But I can preserve a gauge symmetry. That should be a different name. Gauge redundancy, if you wish, by adding additional degree of freedom, as I did in QED. What else? Let me just make sure that I say everything here. Notice, what was the problem with Procka? Was taking MA equal to 0. Okay, a few things. Let's go on. Let's go on discussing this before we move to new. When we did Procka, which meant physical gauge, the propagator once again, delta mu nu has this piece G mu nu minus Q mu Q nu over MA squared. So the problem is the limit MA going to 0 diverges. I don't know how to treat the situation with very high energies. You understand that there's going to be a problem. Okay, forget all this silly language of renormalizability. When I go to high energies, I have a problem. This thing starts contributing more and more. It cannot be. You know, the amplitudes, of course, keep growing like crazy. Now, in this spontaneously broken picture, this was the mass by hand. With the spontaneous symmetry breaking, okay, Stuckebler picture, we can call it, that Hopf picture, whatever, Higgs picture, maybe because it originally started in the Higgs picture, done correctly. Look at our propagator here. Take the limit that may go to 0, it's perfectly well behaved. This is your photon propagator in the arc-side gauge. Of course, in that case, you cannot take psi equal to infinity, because then you would not have a gauge fixing, so you cannot do that in that case. There is no propagator if you don't fix the gauge. Psi going to infinity is getting rid of the. So in the Higgs picture, MA going to 0 is okay. Spontaneous symmetry breaking, this is why we loved it. We say that it's very soft breaking. Soft breaking is on breakings that disappear at high energies. This is Gleshow's dream. Gleshow said, let me write this invariant theory, S2 cross 1. I know I have to break it, but maybe we will understand one day how to make it soft. Soft, it means that the breaking disappears at high energies. Means that I can take the limit of that thing going to 0 and I get a nice smooth limit, and this is perfectly nice smooth limit. So you can work with the spontaneous symmetry breaking, and that means that you can take either V going to 0 or you can take G going to 0. In both cases, MA goes to 0. There are two ways of taking this limit, and they are both perfectly consistent. So let's see what happens. Let's look at it limit a little bit.
Is this limit the same value that goes to the infinity?
Yes. I mean, what is Q? When I say that Q goes to infinity, I'm saying that Q is much bigger than the mass scale in the theory. Okay, that's always, it's a dimensional parameter. So if I tell you that Q is very large or that MA is very small, it's the same thing. In this case, the only scale for me is MA. It's V. There is no other scale. I didn't introduce any other scale. Let's now just keep these propagators. Remember, this is what we are left with. This is what we are left with. Let's try not to erase this. For example, one interesting limit you and I can take is G going to 0. What is that limit, by the way, when G goes to 0? Higgs mechanism becomes Goldstone mechanism, because in this limit, remember d mu? let's write it here. I should also keep it always. D mu is d mu minus I G Q A mu. So when G goes to 0, I'm back to the global case. There is no coupling to the gauge field. So it's like saying I'm not actually taking a local symmetry. Okay, when G goes to 0, I am analyzing the global case. Okay, in this case, d mu goes to d mu, and that means that I'm going back to the global limit. So when G goes to 0, Higgs must go to Goldstone. Now, what is the Higgs mechanism? Higgs mechanism says, I break spontaneously this charge symmetry. The charge did not annihilate the vacuum. What do I get? I get a massive gauge field. I eat 1 degree of freedom. Remember, we said A eats G. There is no G. What is a Goldstone case? Goldstone says, well, there is nobody to eat this guy. So there should be a massless scalar particle, the Nambu Goldstone boson. Let's find it. So how to look at it? Let's look at histopropagators. So what do I have when I delta mu nu goes to what? Q squared G mu nu What is this? This is a massless photon. But notice when G goes to 0, it gets decoupled. There is no this guy. However, this guy is decoupled. Remember that if you write a kinetic energy for some particle and you don't couple it, that the guy doesn't exist. You have to couple it to you and me. Otherwise, forget it. In order if you couple to the matter, you and I are made out of protons and neutrons and electrons and stuff like that. So this guy actually is not there. It's well behaved, that I have no problem taking this limit, but it doesn't interact with anybody. Instead, dq goes to, dg, goes to I over q squared. But that's a massless particle. This is a Goldstone boson, or Nambu Goldstone boson. Even I call it a Goldstone boson. I shouldn't do that. I remember one of my visits here in 1985. I gave lectures, but I also gave a talk. I was asked by Salam to give a general talk on Goldstone bosons. I was working on Nambu Goldstone boson. And I start my talk, and he entered a few minutes late with a distinguished looking Japanese gentleman who looked familiar to me. I have a bad memory of faces. I'm very embarrassed. I always have. It's not just age. I was young then, in 1985. As I keep the Goldstone boson, Salam gets more and more nervous. His face is changing, and I can see that he's getting unhappy, you know. And then he raises his hand, you know, and shouts. It was no shout. He says, can you do me a favor? Can you call these particles Nambu Goldstone bosons? And the Japanese gentleman blushed. It was Nambu, I remember. And it's very embarrassing that I forgot, because he was a friend of Sakita, who was my first boss at City College of New York when I got my PhD. I even went for dinner with Nambu, which was a great occasion. Sakita took us young students with his genius. And my talk actually went very well, because the rest of the talk, every time there was Goldstone, I would write Nambu Goldstone, and the audience laughed, and everybody was happy. Nambu was happy, you know. Salam was happy anyway. I should call them Nambu Goldstone boson. But anyway. So what I promise to you is that we will recover the Goldstone mechanism. So even if you missed it originally, you are now learning once again. If I break a global symmetry spontaneously, I will get a massless particle. How do I see it? Well, look at the propagator of this guy. This is a physical particle now. I cannot gauge it away. There is no gauge field. There is no gauge symmetry. This guy decoupled. So this is a physical particle. Look at its propagator. It's perfectly okay. Does not depend on NXC.
But you say also
Nicholas.
take the same limit as b going to 0.
I can take the same limit as v going to 0.
It's like the expectation value now is 0 and
Right.
no symmetry breaking.
There is no symmetry breaking. So what is happening in this limit? Okay, this is very interesting. So let's okay, there are, let's say A and B. I took B first. B, G going to 0 means decoupling the photon, right? Photon, I'm sorry, I shouldn't call it photon. This gauge boson, okay? That means I'm decoupling it. So that means in this case I'm going to the global limit. What happens in the case A when V goes to 0? Well, I raise my potential. How did the potential look like? Phi squared minus V squared, everything squared. In the limit when V is 0, sorry, why should I? Just that I wrote it, let's keep it. When V is going to 0, obviously, the fields are massless, okay? So I'm also recovering a massless guy, but it's not a Goldstone boson. There is no symmetry breaking. It's massless because I didn't write it master. It's very different from the Nambu-Goldstone situation. Nambu-Goldstone situation, I actually write a master, but a tachyonic master, something very crazy. Then, miracle happens. The thing adjusts themselves. And I end up with a massive guy called Higgs. And the, or Goldstone, that should be called Goldstone, it's funny. Right? He got credit for he didn't discover. Goldstone, get me, find in my book. So, in this case, simply, G is massless since no mass term. It's a trivial thing. If you don't give someone a mass, it's going to be massless. But what is nice that I can go to that limit smoothly. The spontaneous breaking limit is okay going to 0. It's not like hard breaking. That's why we say that spontaneous breaking is soft. It's different from hard breaking. Explicit breaking, you will never cure this Broca thing. In explicit breaking, there is no gauge invariance. There is nothing you can do when there is explicit breaking. There was no fields to deal with. So you would have this. Disappear, you will have the bad propagator. In the case of spontaneous symmetry breaking, that's why Coleman says, there is strictly speaking no breaking. There is a hidden symmetry. Just work with the different variables. The answer of Nambu to Cien Yang in 1960, yes, the symmetry is broken. Well, yes, you are right, it's not broken. Yeah. But it's broken, okay? It depends how you look at it.
So the two limits are giving the same propagators. Or like
Yes, for the two limits give the same propagators for different reasons. Notice that in this limit, the photon exists. It's coupled. It's massless. In this case, there is a massless photon. This guy is not decoupled. If you keep G, then the photon will couple to your fields. Only you have introduced some massless particles, okay, which maybe was not a smart thing to do because we don't see these massless particles, okay. It's not a physical limit, but it's perfectly okay mathematically, it seems. I get a massless scalar field and the photon. So then we should say it here. Decoupling A, right? Well, I said it. Here A stays.
and if I ask in the high momentum limit, which one of this going to happen if you increase energy?
Obviously well, depends if G is 0 or not. You tell me.
G is not 0, but
Then G is not 0, then it cannot be the first case or the second case.
So we
as
can
well.
even distinguish in the high momentum limit two cases.
Of course. No, but that's obvious. If there is... No, but forget all the details. You can always distinguish whether there is a photon or there is no photon. The first thing comes whether G or E is 0 or not. Then we worry about high energy behavior. In the case when G is 0, there is no photon even to talk about. Photon, no gauge boson. So that goes first. And obviously this is not the limit to take, because you want to keep your interaction, okay? You want to keep your Z boson and the W boson. You want to understand what is happening at high energies. So really, this is the thing we are interested in. We can kind of forget that. I just wanted to illustrate that. This is what would happen if you were in the global case. All I wanted is to take this imaginary situation where the symmetry is global. That doesn't correspond to our world. We don't know of any global symmetry spontaneously broken. We are speculating that it may happen, but we don't know. That has not been seen yet. So that obviously I'm not going to discuss this in the future. I will always think of E going to 0 when I want to go to high energies. I will then say, oh, the vacuum potential value is then small because W boson is light. At LHC already you can start looking what happens for, W becomes light. So you can agree, right? The energy is 5 TeV. In the first approximation, I can pretend that W is mass and then do the correction. So this is the way of thinking of the spontaneously broken theory at high energies.
And if we switch the sign in there, it's also another limit instead of minus V plus V.
If I take this plus V square, then of course there is no symmetry breaking. There will be no Goldstone boson.
So
you will see.
Just a massive.
There is nothing I cannot even write in this case e to the IG over V. Well, I can, sorry. What will happen in this case, you will get that mg is equal mh is equal, what is it? Lambda V, right? Square root of lambda V. I will have the degenerate set of states, and I will have a massless gauge field because the minimum would be at phi equals 0. No, I should let me keep this potential. The minimum will be at phi equals 0 if I change the sign, and nothing interesting would happen.
But when you say there is this critical temperature, is
right.
When you change that sign?
Yes, precisely. So this was asked, not all of you were here, so I can erase this. We will be discussing this explicitly when we do some examples. You don't have to understand everything today. Try to get as much as possible because we will be continuing along these lines. So what turns out, when you go to high temperatures, then the potential knows about the temperature. And it's not an easy thing to understand. I remember there was a work, and it was 1974 when Weinberg wrote a beautiful paper, and Shaquille and Dolan, and Shaquille came to City College. I was just starting my research. And Sakita, this friend of Nambu, who was our boss, Shaquille is talking about the temperature all the time and the potential at high temperature. So after about half an hour, Sakita asked him, what do you mean by temperature? And he took his jacket off, when it's hot, and I take my jacket off. Okay. It was a nice friendly exchange because it's not obvious what I mean by temperature. It's a statistical ensemble kind of definition, and I have to imagine a situation with a lot of quanta of this particle, and then I have to do this statistical analysis. So you can imagine that it's not trivial. The bottom line, if the temperature is very large, so what is very large here? Tell me, how can I define large here? T should be much bigger than what? Than V. That's the only scale of the theory. If T is much bigger than V, which is the mass? Okay, I will get V0, this potential, V. So let me write it, lambda over 4. Phi square minus V square, everything squared. I'm glad you asked. This is not really a question We can discuss here seriously, but at least you should know. It turns out, you shouldn't be surprised dimensionally if you say, I don't know anything. But if the temperature very large is the only mass scale of the theory. So that I would guess that I get a term like this. And you get the bottom line of this complicated thing. And the coefficient is proportional to lambda. Let's say the same lambda over 4 or 2. I don't know. There is some coefficient here. It's not 1.
So actually we can write some new V which depends on temperature.
Here it is. Vt is this.
And we can force it to be 0.
Well, we know what will happen. Imagine that T is very large. What will happen? This will become negligible. If T is sufficiently large, this will dominate. I can then ignore this in the first approximation. You agree? The critical temperature is of order V. In this case, the critical temperature will be precisely V. When Tc is bigger than V, phi 0 is 0. There is no spontaneous symmetry breaking. The mass term becomes positive. We looked at that potential.
This is the value universal.
When Tc is less than V, phi 0 is non-zero. And it will be given, phi 0 square will be given by V square minus T square, something like this. I'm sure. Right? Because T square is there. Okay? In other words, I could write this. I could have maybe just to make it. Okay, let me, before I write it, why don't I just make it more user-friendly? So this is lambda over 4 phi to the fourth. This is an interaction. Then there is lambda over 4 v to the fourth, a constant. Then there is plus lambda over 2 t square minus v square phi square. So now it's manifest. It gets more complicated when you are near v. I wrote it when I simplified for you. So let's pretend this is the whole expression. So once again, t bigger than v. Now I read, this is positive. Phi 0, 0, you agree? No symmetry breaking. That's obvious. When t is less than v, we said phi 0 squared is v squared minus t squared. And that we're not. So this is the way we think that it took place. Actually, this one can show this through in the standard model. In the early universe, when the universe was very hot, the symmetry was restored. You know, someone said, let there be symmetry breaking. And symmetry was broken. And there was symmetry breaking. Let me use the proper language. And the consequences of this are very interesting, okay? This is a fascinating issue in cosmology, okay? The issue of symmetry breaking at high temperature. It's a beautiful issue and has to do with fundamental questions. The trouble is, and by the way, this is the only way you and I will know that there is a Higgs mechanism directly. In order to know that you live in the water, you have to get out of the water. As I said, you have to be able as a dolphin to do the phase transition and get out of the water and go into the air. So you and I, in order to test the Higgs mechanism, that's going to be our worry. We will have to understand how to test the Higgs mechanism. Because we can't do that, because this temperature, critical temperature, which is of order V, is of order 100 GeV in the standard model. Because the vacuum expectation value obviously is the scale of weak interaction, which is the mass of the W boson, which is about 100 GeV, which is about 10 to the 13, no, 10 to the 9. 1 GeV is, so this is 10 to the 11 EV. So it's about 10 to the 15 Kelvin. And that's very hot. Very, very hot. I don't know which temperatures you remember, okay? Remember it if you wish in GeV, the sun temperature is about MeV. This is 100 GeV. You can simulate these things. You can have scatterings in a multitude of particles, And you can simulate processes at high temperature. LHC has an experiment, L is devoted to that, which is trying to prove QCD, the temperatures of all the GeV. So today we can at best hope, we are still hundreds of orders of magnitude smaller than the, so one day hopefully that will be done, and one day you and I, well, you, maybe not you, so it takes time, takes a lot of time. Look how long I waited all my life for the Higgs basically, active life. We retire early, you know, at the ICTP we retire early, that's the UNESCO rule, which is crazy. We don't retire, we do other things, go to other places, whatever, but we officially. When the Higgs was found, we retired, basically. I and Smirnov, a few months later, that was the same year. And it was suggested before I started doing, I was still in elementary school when Higgs was suggested, so imagine. How long you have to wait, that's the problem of our field. And that may be why many of you want to do formal things, okay? You have to have patience and faith. It's hard to keep faith when you don't see, as you and I know. What else? You can ask questions before I go on. I don't know if I said everything that I wanted to say. I hope so. Or maybe I have to stop. Time flies. I know not to start anything new. I wanted to introduce fermions and so on, but not at 3:30. No, that wouldn't be healthy. Because really, to understand what is going on, we want to see how any of this interact with the matter, right? Once we do that, when we manage, if you and I manage to work out this U1 case completely, you will see that all the physics will be there. Not all the symmetry breaking properties, not all the mathematics, not all the topology and group theory, but all the physics. So, by the way, since I have a few minutes, it goes like this. I have to tell you something interesting. So the high temperature thing goes, Vt, you can write as V of T equals 0 plus 8T squared, phi squared. Okay? And there is a paper by these guys, I said Chakib, Dolan, and Weinberg. A, in general, has a coefficient which depends on lambda. Okay? In other words, you learned about this, about the temperatures with interactions. You see, because without interactions, there will be no way of creating an equilibrium. Okay, particles have to know about each other to create this statistical thing. Then, if there are gauge interactions, you will have plus g squared, and so on and so forth. But looking at the potential, there is just lambda. And you are saying lambda, remember, must be positive. How does the logic go? Potential has to be bounded from below. Therefore, since lambda, and this is proportional to lambda, therefore you conclude here, you want to have a theorem. Generally, you generally think that if T is sufficiently big, phi 0, 0, symmetry is restored. And this was in 1974, these people showed. Some 5 years later, with my collaborator, my ex-advisor, Mohapatra, we were worrying about high temperature behavior of field theory. Looking at what happens to theories in which, for example, parity could be broken spontaneous, or CP may be broken spontaneous, some other symmetries, so not the standard model. In those cases, you normally need two fields. So imagine that, okay, this is just a little story before we close for today. Imagine that I have two fields. So the potential would look like, And it's good that I mentioned two fields, because then there will be terms like phi 1 to the fourth, you agree? Lambda 1 plus lambda 2 phi to the fourth. There will be a term, let's call it lambda 3, phi 1 square plus phi 2 square. If these fields carry charges, then you don't have linear terms. Okay, I'm writing for simplicity. There will be absolute value, right? So the Vt will be V equal to equal 0 plus, and then you will have A1 t squared phi 1 squared plus A2 t squared phi 2 squared. If I have two fields, you agree? Oh, I wrote without absolute value, sorry. Schematically. Okay, how will the A1 look like? There will be lambda 1, but there will be also lambda 3, because phi 1 interacts with itself, but interacts with phi 2 and creates this possibility of interaction. So you get lambda 1 plus lambda 3, and A2 is lambda 2 plus lambda 3. You see, we wanted to imagine the world. We were worried if the symmetry is restored, then it sort of wasn't good. But that doesn't matter why, anyway. So you say to yourself, oh, lambdas should be positive. But actually it's trickier than that. Lambda 1 and lambda 2 must be positive. If you look at exponential. And you must also have lambda 2 minus lambda 3 squared must be positive. So let me write this to make it clear. Let me write this minus lambda 3. To emphasize, notice that lambda 3 could be negative. Or in other words, I can have minus lambda 3 there. Because the potential must be bounded from below. It will always be bounded below if lambda 1 and lambda 2 are sufficiently large. Doesn't matter how negative this is. If they are sufficiently big, they are going to win over that, because they go as the fourth power, and this is quadratic. But that, for example, one of these terms could be negative. There is no problem. So we found out that the symmetries maybe are not restored at high temperature in general. And we talked to some people, and these people told us we were fools. We didn't understand basic field theory and so on. And I remember we were stuck for about a year. We didn't want to publish it, we were scared. And then we learned. And this was the most original thing I think I ever done in my life. I'm very proud of this. Unfortunately, if we then looked more carefully into Weinberg's beautiful paper in 74, he had noted this. He didn't make it any use of that, but he had already noticed in 1974. In other words, since we asked me about high temperature, the behavior of high temperature field theory is a beautiful field that in general you don't necessarily restore symmetry. Maybe eventually they do, because your perturbation theory breaks down, you don't know how to compute, but you can actually keep, even not only that it doesn't restore, then this temperature mass would grow and grow, and we get more breaking.
If one of the A's
It's a beautiful subject.
we know that it's going to be restored, right? Now.
No, in the standard model there is just one field. No, if there is one field, then of course lambda is positive, but in two fields it's not clear. And Weinberg found out there is a system in nature called Rochelle salt. You know, salts, when you heat them up, they melt. They are crystals and they melt. That's a symmetry restoration, if you wish. You go from, you know, what is symmetry restoration? You go to the system which is less ordered, which is natural to happen, because this vacuum expectation value is like an order parameter. So you will tell me when the temperature is big enough, I want more disorder, you know, entropy will grow, and this is logical that I will have symmetry restoration. Well, Rochelle salt, you heat it up and it gets more crystallized. For a long time. Eventually that breaks down. So I will use these opportunities when there is a minute or two to wet your mouth to tell you, which you can get at almost nothing that you learn is true in general. Right? The theorems, these folk theorems, and this is a very interesting field, the high temperature field theory, in case any of you would be interested. And that's enough for today. This was just a little story. So unfortunately, the most original thing that I've done, I think the craziest thing, this is the trouble with doing physics, okay? Most of the times, even when you do important work, someone else is thinking about it. When we worked on our seesaw mechanism, we found out other people later on learned. And this was really painful because we were so excited. First we were told that we were stupid, and then we managed to prove that we were right. It turned out it was not original. Anyway, we can stop here.